All right, hello, eighth graders. This is the concluding video of our of the semester, actually, but certainly of space. And to remind you, the previous video should have gotten you through question number 44 on the study guide. So if you don't have those all answered, make sure that you go back and get up to speed there, and then begin with question 45. Let's begin with prayer in the name of the Father, and the Son, and the Holy Spirit. Amen. Dear Lord, give me wisdom to do my work well, humility to deal with my mistakes, and confidence because you have made me in your image. Amen. In the name of the Father, and the Son, and the Holy Spirit. Amen. Okay, so today we're going to focus, to begin with, at least a little bit more on the solar system. And just to be clear here, guys, we're going through a lot of information. I'm just kind of hitting the high points. Um, this is something that probably you talked about planets in elementary science, maybe. So there's some familiarity, but I try to kind of point out some of the highlights, I guess, of it. So to begin with, we're going to talk about the inner planets. And the inner planets include Earth, from Mercury out to Earth. So Mercury, Venus, Earth, and Mars. But the word really that's used to describe them as far as the planets themselves, and what I'm after on number 45, is terrestrial. Terrestrial means Earth-like. Okay, terra is Earth. Terrestrial means Earth-like. And then if we go through some specifics about each of them, Mercury is named after the messenger god. Mercury is the messenger god, and the reason is we think of a messenger being freaky fast and moving quickly, and that's what Mercury does. It moves quickly, so it would move quickly across the sky. It moves quickly around the sun, and so that's how it got that name. And a couple of other things that there aren't any questions about this, but I think it's interesting to mention is that Mercury doesn't have any atmosphere, and the result of that is that the sun side of Mercury, the side facing the sun, gets extremely hot. But the night side of Mercury, the back side, the side away from the sun, gets extremely cold, even though it's very close to the sun. And the reason is it doesn't have any blanket of gases to regulate the temperature. So there's nothing to keep the sun's energy out during the day, filter it out. There's nothing to keep the sun's energy in at night. So it's super hot on the day side and frigid cold on the night side. And that kind of leads into the next discussion, which is Venus. And Venus, we're going to find out here, has an extremely thick, heavy atmosphere. And interestingly, if we go back centuries before we really knew much about Venus, there were astronomers and scientists who speculated that it could be very much like Earth. In fact, they thought of it as, because they could see this thick atmosphere, they thought of it as being kind of a, potentially a tropical paradise, somewhere that was very warm and hospitable. And as it turns out, the first probes to reach there were from the Soviet Union. I think in the mid 70s or so, reached Venus, and it turned out to be quite the opposite. It was a very hostile environment. There were a number of things. Number one, and the answer to question 47 is that it has a severe greenhouse effect. What's meant by that is energy comes into the atmosphere, but very little of that energy is able to escape back out. And when we talk about the Earth and greenhouse effect, and something that's in the news sometimes, if we add gases to our atmosphere that cause our atmosphere to trap more energy, it causes the overall worldwide temperature to rise. So it's really important that there's a balance of energy coming in from the sun and energy escaping from the atmosphere back out into space. And when that doesn't happen, you have this kind of a runaway greenhouse effect, which is what Venus has, this very pronounced greenhouse effect. So So that's one of the things. And the other thing that the Soviet astrophysicists found out with the probes that reached there, where they only sent back information for a very short time and then they were crushed. There's extreme, extreme air pressure because of that thick atmosphere. The weight of the atmosphere is so great. And the thing you have to remember is these probes that travel into distant areas, they're pretty light. They have to be light in order to go those distances. So it wouldn't have been made very heavy. And when it landed, pretty soon the pressure, it would be like if you had a diving bell in the ocean that had a very thin wall. When you went down in the ocean, it would just crush it. Okay, so the same thing happened here. So extreme pressure and extreme greenhouse effect and acid rain. And we're talking about severe acid rain. But, when we talk about acid rain on the Earth, we say, well, over time that can kill trees and all that kind of thing. But you would have no sense that the rain that was falling on you was acid rain. On Venus, it would be strong enough that you would have that sense. Hopefully you're not getting that sound. I don't know what that is. Okay. Then Mars, one of the extreme things about Mars is this mountain. And the mountain on Mars called Olympus Mons, is the largest in the solar system. In fact, the base of the mountain would be about the size of the state of Nebraska. Just the base of it is that large. And this bottom picture is superimposing. This would be Mount Everest, the largest mountain on Earth. And this outlines Olympus Mons, the largest mountain in the solar system. So you can see how much larger it is, how much broader it is, and how much higher it is. That's Olympus Mons on Mars. Okay, the next thing then, so we went Mercury, Venus, Earth, Mars, and now we're to this area of kind of debris called the asteroid belt. And the asteroid belt exists between the orbits of Mars and Jupiter. And there's a big jump. We have these 4 terrestrial inner planets that orbit relatively closely. Now, when we say closely, we're talking about they're millions of miles apart still. But the magnitude of distance becomes much greater. So this is at least partly to scale. I don't know if it's exactly to scale, but you see how close the 4 inner planets are. And then there's this huge jump from Mars to Jupiter. And you have all of these asteroids, the asteroid belt. And that's probably an exaggeration of the density of the asteroids, but it is. So is that a planet that broke apart or a planet that never formed at that distance? Those are some of the things that are considered. And some of those asteroids are fairly large. The largest, I think, is one named Ceres, Ceres. Okay, so the next planet, which is this is showing the 4 inner planets and their size, and then this is showing Jupiter, Saturn, Uranus, Neptune, and Pluto, which has been demoted from an actual planet to a dwarf planet. But you see that it's showing the size of the sun. You just see a little arc of its size. The 4 inner planets very small, and then you get into these very large, for good reason, called gas giants. And the mass of Jupiter is actually double. So if you added up all the masses of these and all these, the mass of Jupiter would be twice the mass of all of those others together. And Jupiter is, I believe, the king of gods, and named that way because of its extreme size. Okay, so now we're into the other outer planets, and of course Jupiter's considered among those outer planets. Saturn has the most pronounced rings. Now, all the gas giants have rings, but Saturn has the most notable rings. And there's something in the middle here called the Cassini division. named after an astronomer. But anyway, that's rock and dust and ice that creates these rings. Then we move on to Uranus, and Uranus is unique in that if we were talking about all the other planets, and we were talking about them all being in a plane, they would all basically spin like this. But Uranus actually, if you were looking from the sun out at Uranus, it would actually spin like this. So it's like it's rolling along on its side. Okay. So unlike the other planets that are kind of upright and their axis of rotation is actually kind of perpendicular to their orbit, this one is in the same plane. Its axis of rotation is in the same plane as its orbit. So sometimes Uranus is referred to, it's sometimes referred to as the sideways planet because it rolls along on its side like that. And then Neptune. Oh, I wanted to go back and show you something on. So this is a big storm. I think I missed this. This is number 51. This is the Great Red Spot. The Great Red Spot is a giant storm. It's similar to a hurricane on Earth, but it's actually the size of several Earths. And you can imagine the energy that's created that over time, considering that it's gone on since the first observations of Jupiter from the Earth. So really amazing the size and magnitude of that storm. All right, so we're back to, and Neptune also has, this is called the Great Dark Spot, which would be a similar type of phenomena on Neptune. And then the other thing about Neptune is its year is 164 Earth years. So it's been, I mean, when the last time that Neptune was in the same location that it is right now around the Earth would be about the time of the Civil War. So that's how long it takes Neptune to make one trip around. Now we say it's 164 years, its orbital period, but actually its orbital period is 1 year. It's one Neptune year. For comparison's sake, we say it's 164 Earth years, which a year for any planet is the time it takes to go around one time. So when we say that Neptune's orbit is 164 years, it means it's 164 Earth years. It's one Neptune year. But pretty amazing. It's actually not gone around even one revolution since people on Earth first recognized its existence. I think it was maybe 1871. You could look that up. I'm going to check that just because we're talking about the discovery of Neptune. And actually its discovery, it says it was in the mid 1800s that they projected that it existed, but it wasn't discovered. I don't know if it says the year, but that's kind of an interesting thing. They actually figured out indirectly that it existed because they could tell that something about Uranus's revolution wasn't quite right. Something was affecting how it moved, and they figured there had to be some other massive object that was in the same neighborhood, you might say, of the solar system, and eventually they discovered that to be Neptune. Okay, then we have what are called dwarf planets. And for many years, the years I was from 1931 until, maybe, I guess 1930, it says, until 2006, for about 76 years, Pluto was actually considered the ninth planet. But what they found out was that there were other objects in the solar system. This is Ceres. This is that large asteroid that I was telling you about in the asteroid belt. And then some of these are other dwarf planets in kind of that neighborhood of Pluto. And there are some things that make a planet a planet. It has to be the lone thing kind of in its area, or the dominant thing, you might say, in its area. Because, for example, Jupiter and Saturn have have a huge number of moons, but they are the dominant thing. Those other moons are actually orbiting it like any other moon. But they figured out that Pluto wasn't really dominant in its area of the solar system, and therefore wasn't its own planet. It does have a moon around it, Charon or Charon. I'm not for sure how it's pronounced. Charon. Okay. Now, this is a little different idea, and this is something that's really intriguing to astronomers now, or what are called exoplanets. And an exoplanet means a planet of a different star. So we think of planets as being the things that orbit the sun, and the things that orbit the sun are planets. Large objects that orbit the sun are planets. But there are also objects that aren't luminous, that go around some other stars. And so astronomers really try to find things that they say are in the Goldilocks zone. What do you suppose they're talking about when they say a planet is in the Goldilocks zone? Well, if you're familiar with the story of Goldilocks, this is too hot, this is too cold, this is just right. This is too big, this is too small, this is just right. This is too hard, this is too soft, this is just right. So they're looking for a planet that's in the just right place near a star where it could potentially support life as we know it. And, that's just a lot of speculation, but that's the interesting thing to it. They're trying to figure out, based on how large the star is and how far away the planet is, could it be in a position where it could have conditions that would be conducive to life? And the thing to remember about that, kids always have a lot of questions about, is there life on anywhere else in the universe? And I guess my contention would be, to begin with, maybe no. And furthermore, and say, well, there's all this and that. Could there be? Yeah. But part of the reason, I guess, that it anywhere where there could be, it's so far away, and hopefully we've already talked a little bit about those distances, that, I mean, it's speculation. It's going to really continue to be speculation whether there could be living things somewhere else in the universe, just because the distances between are so great. Okay, now moons in the solar system. Here's our moon, and it's probably kind of toward the upper end of average in terms of size of moons. These Ganymede, Callisto, Io, and Europa are famous. They are moons of Jupiter, and they're called the Galilean moons. Okay, so starting with 57, any object that orbits another object would be referred to as a satellite. So Earth is a satellite of the sun. The moon is a satellite of the Earth. Sometimes I think when we consider satellites, we think of, the things that show us the weather on Earth, or the things that we point a receiver at so we can get television or whatever that might be. And those are satellites, but those are artificial satellites. There are natural satellites, and the natural satellites primarily are moons. Now, again, you can consider the Earth being a satellite of the sun because it goes around it, but we usually think of moons as being the natural satellites. So a natural satellite of a planet is called a moon. The first artificial satellite that was launched was Sputnik. That was in the late 1950s, and that's what kind of triggered the whole space race. The United States was kind of threatened. I mean, you can imagine that if we felt like another country had the ability to observe what was going on in our country, or maybe even to attack us from space, something like that, was very intimidating. And so as soon as that happened, and that was during the Cold War between the Soviet Union, or the Soviet bloc of nations, and the United States, or the kind of the free West. So there was a lot of tension and there was a lot of fear, and that only added to people's fear when they found out that the Soviet Union had a satellite that was in low orbit, and so that kind of triggered the United States to kind of ratchet up space exploration, and that's when, in the early '60s, that's when President Kennedy vowed that by the end of the decade that the United States would put man on the moon, and they made it by about 5 months. Okay, so our moon, a little more detail about our moon. The gravity on the moon is 1/6 of the gravity on the Earth. So this girl, if she had a mass, isn't exactly right, because mass is really not the same as weight. But let's say that something weighed 30 pounds on the Earth, it would only weigh 5 pounds on the moon. And as you can see, she's just as large in either place. That doesn't change. The amount of stuff in her mass doesn't change. But how much the Earth pulls on her and how much the moon pulls on her, Earth's pull is 6 times greater than the moon's, or the moon's is 1/6. Okay, some features of the moon. So these are all craters, and those are impact craters. And so as there's very little protection for the moon from there are two reasons that there are so many craters on the moon. Number one, there's no atmosphere like we have. If you've paid attention since we've been out of school, there have been a couple of meteor showers, and those meteor showers, the reason you can see them is those are burning up as they travel through the Earth's atmosphere. It creates friction, and they burn up mostly before they ever reach the Earth. Now, once in a while, there will be one that will hit the Earth, but most of them burn up before they actually reach the Earth. So you don't have that number of craters on the Earth. And the other thing is the moon, because it doesn't have any atmosphere, it also does, or very little atmosphere, it doesn't have any weather. So whatever craters exist continue to exist because there's nothing to erode them away. So even on Earth, where there have been things that have struck the Earth from space, maybe there was a crater, millennia ago, but over time, the erosion or the weathering of it has worn it away, and so it's not as obvious.
What's that?
Okay, there's a place on the moon right here. These are plains, and they're called Maria. And the reason they were called that is Galileo, back in the time when they were first observing the moon, because they were broad and flat and smooth looking, the assumption was that they were oceans or seas, because that's what we had experience with. If we were looking at the Earth from a distance, we could imagine that these broad, flat, smooth areas what they would look like from space, what the oceans would look like. And so they thought that these perhaps could be oceans. Well, they found out that they're really lava plains. So their lava flows flowed out and hardened and made these smooth areas. And the reason that this one is circled on this diagram is that's the one in particular where the first moon landing occurred. And if you're familiar at all with the moon landing, if you ever watched the footage of that, which if you have it, you can find that on YouTube. It's kind of interesting. That was a real interesting point in the history of our country, was the moon landing. And so that particular mare was called Mare Tranquillitatis, or the Sea of Tranquility. So when they landed on the moon, they said the first transmission, people always say, one small step for man, one giant leap for mankind, which is what they said when they stepped out of the lander. But when they first landed, the first transmission was Houston, because they were calling back to Mission Control, Houston, Tranquility Base. And the reason they call it Tranquility Base is the place where they landed on the moon. the eagle has landed, which had kind of double meaning. The eagle representing our country, and the eagle being the lunar module, and so that's what they're referring to, Sea of Tranquility. Okay, so that's the nature of the names of craters and then mare. Okay, so the next thing we should be on number 63, and this hopefully kind of shows the dynamic that's at work there. And so this person that's put on the moon, or this whatever it is, tower, maybe, I don't know, it's supposed to be a person, but what it's showing is that the same side of the moon always faces the Earth. So what we can observe from the Earth via telescope is going to be the same image or same side. Now you might say that you might say, well, then that must mean the moon is not rotating. But actually, it doesn't mean that, because if the moon didn't rotate, as this came over here, it would always be pointed, this side would always be pointed down here, okay? And instead, it's always pointed in, which means it's turning at the same, it's rotating at the same rate that it's revolving. And so that's where we get this, and you maybe heard what people refer to as the dark side of the moon. Well, the dark side of the moon doesn't mean the side that's not lit up. It means the side that we can't see. It means the side away from the Earth. Okay. Now, it's also worth noting that as we look at objects in space, always half of everything in the solar system, the sun is obviously illuminated all the way around because it's making its own light, but everything else, all the other planets and moons and so on, the side that faces the sun is lit up. Exactly half of it is always lit up by the sun. Okay, so we have this line of day and night, or light and dark. Now, whenever one object blocks out the light from the sun to another object, that's called an eclipse. And so in the case of a lunar eclipse, the Earth is in the path between the sun and moon, and it blocks out the light to the moon. And so in that case, we would have a lunar eclipse. On the other hand, if the moon is in the path that connects the sun and Earth, we have a solar eclipse. And so lunar eclipse, solar eclipse, and we have this dark part of the shadow that's called the umbra, and we have this more faint part of the shadow called the penumbra. And you might recognize here that because of the difference in size, the spot that the moon can create a shadow on the Earth is quite small. And that's why when we had the eclipse, when you guys were in 6th grade, it was so unique because the place where this is pointed is very small. And so for us to have that place of what's called totality right north of town here was pretty unusual. Now, something else to note is the the size of the moon and the size of the sun in the sky for us is kind of unique. So we could even say that a quarter, and you can try this, step outside tonight and hold a quarter up, and at roughly arm's length, you can block out the moon with a quarter. So a quarter at arm's length, and the moon at about 250,000 miles, and the sun at 93 million miles are all roughly the same size, because the quarter is obviously really close. The moon's 250,000 miles away, but much bigger. The sun is much, much bigger, but it's 93 million miles away. So that relationship that the Earth and sun and moon have is pretty unique. in that you can have totality, you can have a total eclipse. Now, one other thing to note is how that relates to where the moon is relative to the Earth. So when the moon is over here, this would be a full moon phase. If the moon wasn't exactly in the orbit, if the moon wasn't exactly in the orbital line of the Earth, you would see it elevated. So let's say that you're looking out from the sun. So if you're looking out from the sun, so you're looking from here over this way. And so the Earth is here and the moon is back here. You can't see the moon, right? So that would be a lunar eclipse. But actually, the plane of orbit of the Earth and moon aren't the same. And so normally, the moon would be up here. So as you can see, if you were looking out from the sun, the near side of this, if we're calling this the moon, would be lit up. And if you were on this back side, the dark side of the Earth, you would see that as a full moon. So a lunar eclipse occurs during a full moon phase. On the other hand, like a couple years ago, again, you're at the sun. You have to imagine that you're looking out from the sun. And you can imagine that during this phase, the moon would cast a shadow on the Earth, and that would be a solar eclipse. Except that most of the time it's not in the same plane. So even though it's on the sun side, it's not in a direct line. And so that solar eclipse would occur during a new moon phase. Okay? And you should be on, and we already answered 70. Half of the object is going to be lit up because light can't go around the corner. So all the side that you see here is lit up, okay, or it can be seen from the camera, and everything that you can't see from the camera would be on the dark side. Okay, so the next thing is moon phases. And although, if we look at this, as we follow around, you can see that this is the sun side. And so as we look at this picture, the right side of the moon is always lit up and the left side is always dark. But now we have to imagine when that's the case, what can we see from the Earth? So remember, when we're on the Earth, we're seeing it primarily during the nighttime hours. So as we look out at the moon, when the moon's right here, we're only going to see the shadowed side. So that's going to be a new moon. Then, as the moon begins to move around, we're going to start to be able to see a little sliver of light on, as we would see it, the right side. And we call that a waxing crescent. Waxing means more and more of it's being lit up. Then we get to here where we see half of it. We see half of the moon lit up, the right side of the moon lit up. And that's called the first quarter. You might say, well, why isn't it called the first half if we can see half of it? But the reason it's called a quarter is we're 1/4 of the way around the Earth. So it's called the first quarter because it's a quarter of the way around in its month. Okay. Then as the right side that's illuminated gets larger, that's called a waxing. Waxing again means gaining, waxing gibbous. And then when we have the sun all the way over here, they have the sun shining on the moon all the way over here, and we can see the full circle. You can see the full circle of the moon. This is a really good diagram because these dotted lines and dashed lines right here are showing what the part that you would actually see. So you can, if you were standing here on the Earth, you'd see most of it lit up and a little bit of shadow over here on the left. If you're looking out from here, you're going to see all lit up. Then over here, you're going to see almost all of it lit up except a little sliver of dark. This time, the little sliver of dark is going to be on the right side. Okay? And then we have third quarter, or sometimes it's called the last quarter, but it's 3/4 of the way around the Earth. And so there, as we would see it in the sky, the left side would be lit up and the right side is dark. Okay. Waning crescent. Waning again means less and less. Waxing means more and more. When we see the entire moon, we can see it. It's called a full moon. When we can't see any of it lit up, that's called a new moon. And it takes about 29 days. It takes about 29 days for it to go through all of its phases. Okay. Next thing is tides. And I don't know that any of you've observed tides. Probably many of you've been to the ocean, but maybe you haven't been there to observe, or been there for a long enough period at the beach to observe the water advancing and retreating. But tides are primarily the result of the moon's gravitational pull on the oceans. So you have, in a new moon phase, you have this bulge that's pulling the oceans kind of this way, and full moon phase, same thing, it's pulling this way. During the quarter phases, it's going to pull in the opposite direction. So what you can see is that during a new moon phase, high tide is going to be at noon. Okay. During a full moon phase, it's going to be at midnight. Here, it's going to be at sun up and sundown, right at the shadow line. Okay. Then there's another thing at work. The highest high tides, and that would be right now in this picture, because the sun is pulling in this direction and the moon is pulling in this direction. We have what are called spring tides. Spring tides occur when the gravity of the sun and moon are pulling in the same direction. So these would be spring tides. When the sun's pulling one direction and the moon is pulling the other direction, we have what are called neap tides. Now, during the course of a day, remember that the Earth is going to spin. It's in this relationship to the sun, but it's going to spin every 24 hours. So as we spin, this is us, this is North America. So we would say we're just between a high tide and low tide. So it'd be tides getting lower and lower and lower, higher and higher and higher, lower, 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 higher, higher, higher. So during the course of 24 hours, you have 2 high tides and 2 low tides. Okay. A little bit more about moons. I know we mentioned them briefly. A couple of planets that have things I think are interesting. Mars has just 2 moons, Phobos and Deimos, and they're kind of irregularly shaped. And the idea is that because of Mars' location in the solar system, perhaps these were asteroids that just kind of got captured by Mars' gravity. So it has these 2 kind of, sometimes they're referred to as like potato-shaped moons. Then the other moons that are very famous kind of are the Galilean moons of Jupiter. So these 4 larger moons of Jupiter were discovered by Galileo, thus the name Galilean moons, but they're 4 large moons. And Jupiter and Saturn both have a lot of moons. In fact, they continue to discover new moons. Many years ago, I think they used to say like 23 and 16 or something like that. And now the numbers are way higher than that as they just continue to find with better methods of observation and probes and so on, they continue to find new moons. Okay. Other objects in the solar system, comets. Probably the most common comet that you might be aware of is called Halley's Comet. And Halley's Comet its orbit is this pink kind of a line right here. Well, first of all, let's look at this. A comet's tail, that tail of gas and dust, is always away from the sun. So we always think of a tail as being behind something. But in fact, with a comet, as it travels around, its tail is always going to point away from the sun. So wherever it is, its tail is going to be pointed away from the sun, and that's due to something called the solar wind. Okay. Now, Halley's comet is what's called a sun grazer. It comes in very close to the sun and then goes way out. And as you can see here, 4 years from now, it will reach its aphelion, or its point farthest from the sun, and then it will be see, must have been in about 80, between 85 and 87, that it was very close to the sun. So it comes in very close and then goes very far away, and so it's gonna be, so it will have been, let's see, about it's about 73 years, its period, I think. So it's going to go all the way away, come all the way back, and so it'll be another. It'll be about what, about 2060, roughly about 2060, by the time it gets clear back to here. Okay. Actually, maybe is it 70? Maybe it's 76 years. I might have that number wrong. It might be 76 years. It looks like 48 and 24 were when it was away, so it must be 76 years. So 30, if it was 86, and maybe 2062, something like that. So it'll be a while. But those are comets. Okay, a little bit about the sun and other stars. Stars are actually fueled by a process called nuclear fusion, and that's where two hydrogen nuclei join together and make a helium atom. They fuse, they stick together. When we think about nuclear power on Earth, like nuclear power plants and nuclear submarines that are powered by nuclear energy and things like that, those are done by what's called nuclear fission. That is, we take a atomic nucleus and we split it apart, and that's where we're creating the energy. But nuclear fusion is what fuels stars, and it takes an extremely high amount of pressure and temperature to create conditions where this can happen. If we could ever figure out how to do what they call cold fusion on Earth, all of our energy needs would be pretty much solved, because the amount of energy given off is really tremendous. Okay. So that's nuclear fusion, and so stars are fueled by fusion, two atoms of hydrogen joined to make one atom of helium. Okay. This kind of relates to the thing with a quarter at arm's length, and the moon at 250,000 miles, and the sun at 93 million miles. And the point is, the closer something is to you, the larger it appears. Okay. Well, the same thing is true with brightness of stars. So we could have a very bright star that's very far away, or a less bright star that's much closer, relatively speaking, and they would have the same apparent size, or they would have the same apparent magnitude. But if we're talking about absolute, this large one, we know, because it's farther away and it still appears fairly bright in the sky, it would have a larger absolute magnitude, and this one would have a smaller absolute magnitude. So apparent is what it appears to be. What does it look like from the Earth? That's apparent magnitude. And absolute magnitude is how bright it actually is. So a good way to think about that is, if a doctor looks in your eye and he has a pin light and he shines it to see if your pupil is adjusting, it's super bright because it's like 2 inches from your eye and he's shining it right in your eye. That has a very high apparent magnitude, but a very low absolute magnitude. Okay. You could go outside tonight and look at a star in the sky, and you don't have to squint at all if you look at a star, because its apparent magnitude is very low. But in reality, that star's absolute magnitude would be way, way many billions of times brighter than that pin light that your doctor is using to look at your pupil. So apparent is what it looks like. Okay, so it's a combination of how bright it is and how far away it is. And absolute is, if we're going to compare absolute magnitudes, what we're really saying is, how would it look compared to these other things if they were all the same distance away? Okay, that's apparent and absolute magnitude. Okay, stars. We think of the sun. It's obviously, in terms of apparent magnitude, it's easily the brightest thing in our sky by many, many factors. It's the brightest thing in our sky. But in reality, our sun is fairly average in terms of its brightness and its temperature. The hottest stars are blue or blue-white. Yellow, like our sun, is kind of a medium temperature star. And then the coolest stars are red. So 40,000 degrees Celsius. And all of these temperatures are still, in Earth terms, are extremely, extremely hot. I mean, it's only in terms of stars that we can say that something that's 3,000 degrees Celsius is cool comparatively. But if we look at 40,000, it is kind of cool comparatively. All right. Distance to things in the solar system, distance to things in the universe, I should say. Light years. I think this is let's watch just a little bit of this. It's not very
confusingly,
long,
light years are not a measure of time, but distance. Huge distances, especially those in space, where kilometers and miles just don't do the job. So scientists use the light year. Very simply, the distance light travels in a year if there's nothing to slow it down. Radio waves, what we look at here at Jodrell Bank, travel at the same speed. So if light travels 299,792.458 kilometers in just 1 second,
and that's usually just 300,000 kilometers. They round it up.
Over a year, that's 9,460,730,472,580.8 kilometers. And to get an idea of what that means, let's take the Earth and the Moon. In space terms, they're very close.
How long would you say it would take light to reflect from the moon and get to the Earth? That's what he's kind of speculating.
About 380,000 kilometers apart. Light takes just over a second to travel between them. So this distance,
it's like 1.1, 1.2 seconds, something like that. So as far as the moon is away, it only takes a little over a second for light to travel between the two. So now we're talking with light years, we're talking about it taking years for light to go that far. So
is about a light second. The sun, however, is a bit further away, about 100.
How long is it going to take light to get from the sun to the Earth? Make a guess at that.
150 million kilometers. Light takes about 500 seconds to travel from there to the Earth. That's about 8 light minutes.
Okay, it takes about 8 minutes. And I think I had a question earlier here that if the sun burned out, we wouldn't actually know it for 8 minutes. That picture that we're looking at of the sun coming to our eye would continue to travel here for 8 minutes.
Further out, our most distant space probe, Voyager 1, has traveled almost 17 billion kilometers to the edge of our solar system. But that's still only about 16 light hours away. Head out of the solar system, and the next nearest star, Proxima Centauri, is about 40 trillion kilometers away. And this is where light years start to come in handy, because we can just forget about all these zeros and just say about 4 light years and stop.
Okay, so when light, if you were to find Proxima Centauri in the sky, This is the one where I said the when that light left that star, if you were to find that star in the sky tonight, when the light left that star, it's been traveling from that star to your eye since you were in fourth grade.
Stop there. Or not, and instead head to the center of our galaxy, the Milky Way. Or Andromeda, the next big galaxy along, which is a long way away. But also, when we look...
So if we said Andromeda, the Andromeda galaxy, let me see if I can get that back here. Okay, 2.5 million light years. 2.5 million light years. Okay, so just kind of unfathomable.
Long, which is a long way away. But also, when we look at it, a long time ago. Because when I look at Andromeda from Earth, I'm seeing it as it was 2.5 million years ago. Because that's how long it took the light to reach me. And that's a light year.
Okay, so hopefully that gives you some sense of just the immensity of the universe. It's just really hard to get your mind around. Okay, so Polaris here, it's showing the North Star is about 400 light years away. Now, Polaris is at a distance that we might be able to have some ability to estimate its distance based on the angle that it's at in the sky. The reason Polaris is an important star is it was used in navigation because it was in the northern sky. It basically would be where the axis where the North Pole of the Earth would project into the celestial sphere or into the sky would point at Polaris or the North Star. It's about 400 light years away. So if you were to find the North Star tonight, the light that is leaving the North Star, the light that you saw left the North Star 400 years ago, about the time of the first settlements of Europeans in North America. Okay, now the last thing we're going to talk about is the origin of the universe. And the origin of the universe was first conceived by a priest named Georges Lemaitre. And we're going to watch just a little bit of that.
He was a Belgian priest, a cosmologist, an astronomer, and a mathematician. Father Georges Lemaitre earned a PhD in mathematics from the University of Leuven in Belgium in 1920, and he was ordained a diocesan priest 3 years later in 1923. He went on to earn advanced degrees at Cambridge under the direction of the great scientist Sir Arthur Eddington, at Harvard College Observatory in Cambridge, Massachusetts, and at the Massachusetts Institute of Technology. It was in 1927 that Father Lemaitre's work would begin to send shockwaves through the scientific world. That year, he published an article in French entitled "A Homogeneous Universe of Constant Mass and Growing Radius, Accounting for the Radial Velocity of Extragalactic Nebulae." He was the first scientist to propose the idea that the cosmos is expanding. When, with the help of Arthur Eddington...
Now, here's the idea of the universe expanding. That's kind of the root of this idea of the Big Bang. If we ran that in reverse, think about if you had, and maybe you've seen like super slow-mo photography of a firecracker bursting. Well, as it's bursting and moving apart, if you move that in reverse, it would all come back together, right? So the idea here is that if everything is spreading out and you run that kind of in reverse, then everything would have started at a common center point.
That article was translated into English 4 years later. His proposal got the attention of Albert Einstein and many other major scientists and mathematicians. Einstein initially refused to accept the idea of an expanding universe, and he told Lemaitre, "Your calculations are correct, but your physics is atrocious." At a conference in London in 1930, Lemaitre offered a further proposal that the universe expanded from an initial point, a singularity, which he called the primeval atom. He sometimes called this theory the cosmic egg exploding at the moment of creation. He was the first scientist to propose not only that the universe is expanding from an initial explosion, but that the rate of that expansion is actually accelerating. A British scientist named Fred Hoyle, who, like Einstein, was a stubborn proponent of the static, steady-state universe, went on BBC Radio to mock Lemaitre's theory by sarcastically calling it the Big Bang Theory. Even Father Lemaitre's mentor, Sir Arthur Eddington, was unconvinced.
Interestingly, someone used the term Big Bang to mock the idea, and eventually it was shown to seemingly be true.
Lemaitre had met Albert Einstein on 3 occasions, twice at conferences in Brussels and once at Princeton University in New Jersey. In 1935, the two men traveled to California for a series of conferences. After hearing Lemaitre fully explain his expanding universe theory, Einstein stood on his feet, applauded, and said, "This is the most beautiful and satisfactory explanation of creation to which I have ever listened." Using Einstein's own mathematical constructions, Lemaitre had changed Einstein's mind and convinced him that the steady-state universe was untenable, that the universe is indeed expanding. So Father George Lemaitre was, among other things, a pioneer in applying Einstein's theory of general relativity to cosmology. Although for a long time Edwin Hubble received credit for what became known as Hubble's law, we now know that Lemaitre proposed it 2 years earlier. Since it was published in French, it didn't reach the English-speaking world for several years. For good reason, newspapers around the world began to call the Belgian priest the leader of the new cosmological physics. His work changed the course of cosmology. By the way, Lemaitre was a modest man who said it didn't bother him at all that Hubble was getting credit for his ideas. Lemaitre's most famous book on the subject was published in 1946, The Primeval Atom Hypothesis. Over the years, Georges Lemaitre received any number of honors, becoming a member of the Pontifical Academy of Sciences and the Belgian Royal Academy of Sciences and Arts, and receiving the Eddington Medal from the Royal Astronomical Society of Great Britain. Just before he died in 1966, Father Lemaitre learned of the discovery of cosmic microwave background radiation, which provided further evidence for his primeval atom theory. So, as the poster in the meme proclaims, if you like the Big Bang Theory, thank a priest. And by the way, if you are under the impression that Christian faith is hostile to and an enemy of science, that impression is wrong. It may be true for a small number of Christians who insist on interpreting every word of the Bible literally, but it has never been the case for mainstream Christians, including Roman Catholics. Along with Father Gregor Mendel and Father Teilhard de Chardin and thousands of other faithful Catholics involved in scientific research, Father George Lemaitre was a living example of the compatibility of reason and Christian faith, science, and religion. Let us pray. Lord, help us to see that we learn about you in many ways. We learn about you when we place our faith in the words of your prophets and the written scriptures which you inspire. And we learn about you by using reason and logic and the scientific method to probe more deeply into the cosmos you have created and continue to create. You, Lord, are the source of everything that is true and real. Help us to understand, as St. Augustine did, that what we know by faith and what we learn by reason cannot be in conflict. Continue to challenge each one of us to grow and to reach our potential, both spiritually and intellectually.
Okay, guys, I think that's a good way to end this discussion and a good way to end our school year with that challenge that we as the pinnacle of God's creation need to have an appreciation that all things are in fact created by God. As Christians, we understand all of creation is the work of God, the Creator God, and there's a challenge in that for us to maximize our learning, whatever area of interest we have, to challenge ourselves to learn about it and see the wonder of all of God's creation. So with that, please complete the study guide, and I look forward to seeing you soon. Have a blessed and safe summer, and again, hope to see you soon. Blessings.